Well, hi, everyone. Thanks for joining this webinar for everything you need to know about automotive multi-gig Ethernet. My name's John Simon. I'm a product and applications manager at Intrepid Control Systems for automotive Ethernet products. So what I'm going to go through in the next half hour or so is what exactly is MultiGBASE-T1, and do we really need it? We're going from 1 gig to higher bit rates. What is driving that in the in-vehicle networks design? Then I'll go at a high level, how does this work? The physical coding sublayer and the processor interfaces, the connection systems that will be associated with MultiGBASE-T1, the interoperability testing and compliance standards that are available and others that are in draft. And then I'll give some, hopefully what you find practical knowledge in working with MultiGBASE-T1, and followed by the types of tools that we're going to be going into production with for working with MultiGBASE-T1 products and our roadmap for similar products. And then lastly, does this stop at 10 gigabits per second? As you probably guessed, the answer is no, but I'll give a little bit more information about what the activity that's going on in that space. So what is MultiGBASE-T1? It's captured in the standard 802, or the amendment to the standard 802.3 in the amendment 802.3 CH 2020. It defines full duplex 2.55 and 10 gigabit Ethernet communication on a single shielded twisted pair up to 15 meters, and will also accommodate up to 4 inline connections between one device and another. It's known collectively as MultiGBASE-T1, but there are 3 speeds that you can refer to the specific speed by 2.5G base-T1, 5G base-T1, or 10G base-T1. It does have some optional aspects of it related to auto negotiation of the master slave, the clock source of the connection, as well as energy efficient Ethernet that supports idle and power saving modes for use in automotive ECUs. Now, why do we need this? We're at a point where we're moving away from what's called a domain architecture. This is an architecture that was added some obvious improvements from previous architectures as the technology advanced, and it's segregated by its the domains are segregated by independent networks. So you can see in this diagram, each of the colors represents a different domain, and those the colored networks are networks specific to that domain. So you can see there are a lot of redundant or parallel networks going from one end of the vehicle or one region of the vehicle to the other that could be combined and optimized. So in recent years, advances in technology have made this architecture suboptimal in terms of cost, weight, and manufacturing. Okay, see a question just popped up. Will this cause the ability to use grass marlin against canned moot, being higher transfer rates than the old sniffer? I guess I'm not familiar with grass marlin but I wouldn't say that this is at this point Ethernet's going to replace CAN. There is a technology 10 base-T1S that is going to, it would seem it's being it could replace CAN depending on the OEM's requirements, but that's kind of beyond the scope of what we're talking about here. There was a webinar last week that goes into detail about 10 base-T1S. You can probably find a link to a recording on LinkedIn. So moving to zonal architectures. Zonal architectures are replacing domain architectures, and just the goal of any new architecture is to optimize power and signal distribution systems. And in this case, there are fewer network connections, less cost, less weight, simpler assembly, and higher reliability, mechanically speaking, in terms of the less number of cut leads in the wire harness, the less number of wires to cut, for connectors to be become unseated, terminals to become bent. And so what you can see in this diagram now is we still have 3 domains representing colors, but by and large the vehicle is connected all of these domains with a backbone represented in the green boxes and lines. So you have some central computing modules connected over a backbone to all of the same ECUs and sensors that were in the previous diagram, but now these are connected via gateway modules. So you can see there's a much less cabling, much less connections, but this optimization does have a cost of naturally you require higher bandwidth. The connections between the gateway modules to the processing or compute modules need much higher bandwidth to carry all of the traffic that was carried in the multiple networks in the previous slide. You also, with combining all this, you need quality of service guarantees. This is because you're sharing bandwidth between subsystems. You have more failure modes and more fault conditions. Another thing that's driving the need for higher bandwidth is the cameras for autonomous and autonomous driving and ADAS systems. The direct trend is to use unprocessed or uncompressed video in the cameras to take the cost out of the cameras, minimize the heat, and make these cameras more of a commodity instead of a specialized device. You can also manage the latency of the processing, any video processing of the video by centrally doing this in a central ECU. And you can see by this chart here that anything over 720 is rapidly approaching 1 gigabit per second. And depending on the color depth and your frame rate, you're over 1 gigabit per second. So if there's any intent to stream uncompressed video, you're probably not going to do it on a 1 gigabit link. So the current, there's also a desire for a more homogeneous network. Currently, the mainstream approach for connecting cameras to a network is through SerDes or serialization, deserialization. This is a point-to-point connection between an ECU and a camera or sensor, and this differs from Ethernet, and so it makes the overall network less homogeneous. Another factor is redundancy. Going back to the slide earlier where I talked about needing quality of service guarantees, one of these mechanisms for ensuring quality of service is redundancy or frame replication and elimination for redundancy. So now you're adding or increasing the traffic on the network by adding redundant frames, and you're effectively doubling the bandwidth consumed by any specific stream. So here's a diagram of history and trends of in-vehicle networking from Dr. Kirsten Matthews. And you can see CAN has done well through the 90s, had a pretty, well, it's linear, but this is a log graph, but you can see kind of a linear line here as it approached above 1 gigabit and 1 megabit and 10 megabits. And then here is the Automotive Ethernet in-vehicle networking, and this is the SerDes. So you can see in the higher bandwidth connections for SerDes, we can replace those with 2.5, 5, and 10 gigabit, and possibly even 25 gigabit. So this occurred to me when we first started investigating multi-gigabit automotive Ethernet. Why not go right to 10 gigabits? Why even bother with 2.5 and 5? Well, cost is the obvious answer, but it's not just the cost of the PHY. Someone pointed out to me that when you look for a microcontroller, microprocessor with a MAC interface that supports greater than 2.5 gigabits per second, your selection, the number of components available to support that is lower and also much more expensive. And then also risk. Generally speaking, if you use a device at some margin below what it was designed for in terms of its maximum ratings, there's a reasonably good chance you'll encounter less problems. At least in MultiGBASE-T1, you would be using lower frequency designs, and you would have less thermal management to contend with. So how does MultiGBASE-T1 work? How is it different from the 100 and 1000 base T1? To start, the physical layer is different. It uses PAM4, pulse amplitude modulation with 4 logical states. Each state encodes 2 bits, and the states, there's a 2 volt span across all these states, which means each logic level or each logic state is 2/3 of a volt from the neighboring logical states. And it runs at a clock frequency of 10 for 10 gigabit, 5.625 gigahertz. Half of that for 10 gigabits per second, the clock is 5.625. Half of that for 5 gigabit, and half again for 2.5 gigabit. Now, if you do the math, 2 bits times 5.625 gigahertz is more than 10 gigabits. And this is because there's about 10% overhead for error correction. I'll explain that in a little bit in future slides, but there's more information being transmitted than just the data. Modulation. So why PAM4? 100 and 1000 base T1 or PAM3 or 3 logical states? Well, adding additional PAM states or different voltage levels, you increase the bit rate without increasing the frequency. So you're able to transmit more information without increasing the frequency and running the risk of EMC emissions or susceptibility, or emissions. So this eye diagram here, this is a superposition of all of the logic states that could occur on the physical medium. So these red lines here represent 1 volt staying at 1 volt, 1 volt going down to one third of a volt, and so on, -1/3 and -1. And then each of these are representing the transitions from -1, all of the other states, to 1 volt. And what you'll see here is this is effectively your signal to noise ratio, or correlates with your signal to noise ratio. So for every additional state you have here, this window here shrinks. So you're effectively reducing your signal to noise ratio and making your network more susceptible to errors due to EMC interference. Now, PAM4 was specifically chosen for balanced performance for all 3 of the speeds, 2.5, 5, and 10 gigabit, using the 15-meter cable. If you want a more detail of all the trade-offs that were investigated, I put a paper down here that goes through it in great detail. And basically, they came up with something that has the optimal bandwidth and gives the maximum signal to noise ratio, and also balancing power consumption and interference tolerance. In 1000 base T1, or sorry, MultiGBASE-T1, there's the physical coding sublayer, and that is the transformation or encoding of the information between the microprocessor and the information that goes out on the wire. So there's much more on the wire than just the data. It uses something called 64B, 65B encoding, or 64 bits, 65 bits. And that means 64 bits are represented in a block of 65 bits. And this allows control information to be interspersed with the data. There's also some optional OEM control data, and this stands for operations, administration, and maintenance. And then lastly, the forward error correction that I alluded to earlier. This is required to achieve the bit error ratio desired of 10 e to the -12. And so this Reed-Solomon forward error correction can correct up to 17 symbols that that have been affected by errors. And this represents an additional 10% overhead. There are other ways to manage achieve the bit error ratio. You could increase the transmit power, but then you have, you're increasing the power, you're also affecting your EMC performance as well. There's always a number of trade-offs. In this case, the trade-offs favored using this forward error correction at the cost of 10% overhead in the bandwidth consumed by this error correction. So ultimately, what goes out on the wire are 3600 bit blocks, and that consists of 50 65-bit blocks plus 10 bits of operations, administration, and maintenance, and then 340 bits that are the error correction bits. So for every 3,260 bits of data that go out on that are being transferred between devices, that's represented in a 3600-bit block. Now, there's some additional noise immunity tactics that are done at these high data rates. One of these is called interleaving, and so many sources of noise are short-term bursts. And so this interleaving of data reduces the number of corrupt symbols in any one block of data during these bursts. And it's a little easier to see graphically, but what this does is it helps the forward error correction be much more effective. So you can see a series of blocks here, there are no interleaving. So you block 1, block 2, 3, and 4, with some interference in data block 2, it affects this entire block. If you are to take this same information and then interleave the packets every 4 packets and interleave those, now this interference is spread across the 4 different blocks of information, and now you have a better probability of the forward error correction being able to correct the errors. Recall that it can correct up to 17 symbol errors. Some additional functions of a physical coding sublayer. There's a 33-bit scrambler, and this is common to all of the other 100-base-T1, in that it's there for 2 reasons. One, for EMC optimization. If you have a recurring bit pattern that's being sent, that will correlate to higher power emissions in certain frequencies. So when you scramble it, it makes it a pseudo random sequence, which spreads that power over a wider band of frequencies. It also ensures logical transitions. In order for clocks to remain synchronized, you need edge or transitions between states. And if you have runs of ones or zeros for a period of time, you would be concerned with things falling out of synchronization. There's also some gray mapping, and this is a simple trick to minimize the impact of a single flip bit. You can see here decimal 0123 encoded in straight binary. If this red 0 here were to flip, the error results in the magnitude of the error of 2. So what they've done for this gray mapping is to just swap or reorder the values of the mapped information to the decimal information. So now you can see if the same bit were to flip, now the error is 1 instead of 2. And then lastly, there is something called a selectable precoder. This is something that during the training phase, or training period of 2 PHYs linking, there's this ability to kind of characterize the behavior of the link. And then there are some pre-coded or a precoder or a filter that can be applied, and it can increase the performance of the link in terms of bit errors or fewer bit errors. So we've been working from the physical medium up. We talked about the pulse amplitude modulation on the medium, and we've talked about the physical coding sublayer in the PHY. So how is the PHY connected to microcontrollers. Well, if you read the spec 802.1ch, it references XGMII, X being 10, and then gigabit media independent interface. This is not really an interface that is the best for connecting one chip to another. It's actually an inter-chip interface with 32 signals. So 32 signals running across the PCB at high speeds. It's limited to a range. So MultiGBASE-T1 PHYs support one or more of the following interfaces that it's called a reconciliation layer between the PHY and the MAC layer of the host device. So one of these is XFI, and this is a standard that was came about for SFP modules, and these are pluggable or plug and play PHYs that you can see in test equipment. It's basically a slot where you, instead of a RJ45 connector or 100 base or 1000 base T1 or MultiGBASE-T1, you can switch different PHYs and different connectors out. And this is only 4 signals versus 32 of XGMII. And it supports up to 10 gigabit data transfer. Some devices support 2.5 and 5, but the excuse me, this does not support 1 gig and lower speeds. There's the USXGMII, and US is I think Unified Serial 10 gigabit media independent interface. This is something that was a Cisco standard. Again, it's 4 signals versus 32, and roughly, well, the same clock speed. And this does support the lower clock speed. So it goes from 10 gigabit all the way down to 10 megabit. And really, which one of these you use will depend on the PHY that you choose. Some PHY silicon suppliers will support exclusively XFI. Others may support one or both of these. There's also an older one. This is pronounced Zowie. I forget what it stands for. It's an IEEE standard, but it seems to have fallen out of favor just because it's a lower clock speed, which is attractive, but it's got 4 times the number of signals. So how are we going to interconnect all these ECUs to switches and to the vehicle? IEEE doesn't specify automotive connectors and cables. The Open Alliance, TC9, the Ethernet channel and components, they define the cabling channels and the component parameter limits, preserve and fulfill the link segment requirements, and specify how to test application-independent test methods. But at least to this point, for 100 and 1000 base T1, interoperability between connector and cable suppliers hasn't been a priority. Unfortunately, MultiGBASE-T1 connectors and cables, we should see some commonization. US CAR is specifying requirements for a common 10 gigabit per second connection system. These are, so it will, it's specified as 1, 2, 4, and 6 cavities, a common PCB footprint, and common mating features. And right now, Rosenberger's HMTD meets these requirements. TE has a similar computing technology, GE or GEMNet, and then I'm sure there will be others that will take the US CAR requirements and come up with their own connection systems that meet these requirements. So I've explained how this technology works, but when you're working with it, what kind of problems, what could possibly go wrong in working with this new technology? Obviously, this is something that the first assumption everybody jumps to is the interoperability issues between initial PHYs. So right now, every OEM in Tier 1 is trying to get the earliest hardware available. So the problem is achieving interoperability can be, or exclusive, it's always an iterative process. First silicon is never production silicon. There are iterations to meet requirements, and there's also can be PHY configuration firmware tweaks that maybe they don't have to do a full turn of silicon, but they need to tweak or tune the firmware. So these types of issues will undoubtedly surface, but I don't expect them to be the root cause of many problems that arise. A vast majority of issues will be no different than the current and past technologies. Most common linking problem, this is an exchange I had with our tech support. He sent me a picture and said, rate my customer's AE connection. Would you expect any connection problems with that? And my response was, well, it's not ideal, but it might work, it might not. He says it kind of does, kind of doesn't. It seemed to randomly lose connection. And that's exactly what I would expect. And then we make a little joke. It's called single twisted pair for a reason. And he responds, I think there's a single twist in one of them. So by far the most common problem with linking is independent of what speed it is. It's 100,000, and I expect it to be equally as common in multi-gig. Is just the cabling having a good termination of the cable, good turns per inch of the cable, good shielding. And I realized that in development, you end up needing to make your own cables for instrumentation. You may not have the proper crimp tools or the proper experience to construct the cable you need, but I think by and large, these are the types of problems we have. And something like this, as it said right in the chat, sometimes it works, sometimes it doesn't. I've made cables, modifications to cables, and was completely surprised they worked at all. And then I've sat down and done some things where I spliced into a cable and took my time to make sure that all the crimps and everything worked perfectly and had very poor performance. So if you can have the cables made by a cable supplier without having to modify them, I think you will have far less problem or less probability of having problems. Less common linking problems. The plug and play consumer world, at least from my perspective, has made us engineers kind of soft. I think the entire world is used to just plugging things in and they just work through auto negotiation, Ethernet, you have USB, everything just magically enumerates. Automotive is more of a plug and pray environment. And if your prayers aren't answered and you plug things in and they don't work, the first thing I would check into is configuration mismatch, link speed or master slave. When in doubt, turn off the auto config on a device, or at least if you can't turn it off, at least confirm the state of the configuration that resulted from the auto config, and then double check any or triple check any static configurations. Other issues, less common, but I've seen benches where they were trying to debug a link issue and the device wasn't powered, or it didn't have firmware, or it was powered up and everything looked like it was supposed to work, but there was actually a CAN simulation that wasn't running. So the DUT that they were trying to test Ethernet just wasn't even powering up the link because it thought it should be in a different power state. And then some problems remain a mystery. And I say, to me, a lot of times I'll get calls or work with our customer support to root cause and troubleshoot link issues. And a couple days later, we just stopped getting calls. So apparently, I assume the problem has been resolved, but I never hear back as to if it was cable or configuration or an auto configuration issue. But I highly suspect that it was one of the more simpler problems. Usually, by the time you get a piece of hardware in your hand or a test tool in your hand, at least from the board design perspective, it's been tested to meet the insertion loss requirements and the return loss requirements that are needed to ensure a good, proper link. Anticipated problems. Well, at these high speeds, there's going to be any number of bottlenecks. First one I see, and I've seen this quite a bit with even just 1 gigabit, you have a network adapter that links it the speed you expect, but it doesn't support the full data rate. So, and this is often masked by TCP/IP if you're just using it for normal, internet access or something, just web access. You don't see this because TCP/IP is going to request the information again for the application. You may need Thunderbolt or a PCIe NIC to get the full 10 gigabit speeds. But this is just an example. This is just a quick benchmark I did of a gigabit USB 3 adapter. And this I've seen also plugged it into a lower speed port. So this is a gigabit adapter plugged into a USB port, and it's getting 2 to 3, between 2 and well, not even 3, a little over 200 megabits per second. And USB 2 advertises 480 megabits per second, which is theoretical. I wouldn't expect that, but you can see this is less than half of that. That same adapter I plugged into a USB 3 port, and I was getting on the order of 700 megabits per second, which is pretty good. But if you're expecting a USB or this type of adapter to get the full 100 meg or gigabit, you probably won't. And I've seen cheap Ethernet adapters where it just basically clamps at 125 megabit. There was something in that device that just couldn't handle throughput more, and it would just drop frames. And then this is Thunderbolt 10G adapter, and you can see I'm only getting 2 or 3 gigabits per second on this particular benchmark. So if you're any new setup, any new piece of test equipment or laptop that you're using for your development, you need to benchmark it and understand if there are bottlenecks and where they are, and if they don't support the bandwidth that you need for your development, need to look for alternatives. And bandwidth isn't the only potential bottleneck. If you have a high frame rate or number of frames being sent, you can overwhelm any processor that's receiving those. And I've seen that more. I've seen problems well under 1 gigabit, and the problem was it was small frames, 64 to 128 bytes, but the number of messages per second was the problem, not the bandwidth. Anticipated problems, additional problems I could see: backward compatibility. Many 1000-base-T1 PHYs support 100-base, but not all of them. Similarly, MultiGBASE-T1 PHYs may or may not support speeds lower than 2.5 gigabit. At least for the devices that we have now, the Marvell PHY supports 2.5, 5, and 10. It does not support 1 gigabit. I'm aware of at least one supplier that is going to support below 2.5 gigabits, but I can't really discuss that in any detail. Also, proper network adapter or NIC configuration. So auto negotiation may not work if it's not enabled on both PHYs. That's just how the auto negotiation works. Both PHYs need to have it enabled when you connect them. A media converter set to 2.5 gig is not likely going to have auto negotiation enabled. So if you plug that into your computer, which probably has auto negotiation enabled, or your test equipment, you may have a link problem. Or it may look like it's linking, but it should behave properly, but you'll get some erratic performance. So in most cases, I would make sure that your PC or whatever device that you're using to talk to the DUT, if you're using a media converter, have that statically set if you can. So the initial step to resolve linkage might be looking at static speed settings, but I can't emphasize enough, always check your cabling. Testing, by and large, it's been adapted from the MultiGBASE-T1 testing requirements. So you have PMA transmit tests, the output droop, linearity, jitter, power spectral density, peak differential output, and then the clock frequency. PMA's receive tests, so verifying the bit error rate, noise, crosstalk noise rejection, and then there's an optional receiver frequency tolerance, and then a return loss, MDI return loss. So if making sure that you have the matched impedance and you're not losing power in form of reflections back from the media. There's advanced diagnostic features. They're also mostly adapted from MultiGBASE-T1 testing requirements. So you'll still have the dynamic channel quality, so signal noise ratio, signal quality index, which is it correlates with the bit error ratio, and then the spectral emissions. This is an optional diagnostic feature. Harness defect detection. If you haven't used this on gigabit, it's really interesting. It's able to not only detect if there's an open or a short on your link. It can use time delay reflection of signals to estimate how far away from the connection at your ECU the fault is. And I've played with it. It's remarkably accurate, with some caveats on like you can't have bends in the harness beyond. You can't basically bend the harness back against itself. But if you have a straight harness or a harness that has relatively reasonable bend radiuses, it's remarkably accurate. Link quality, so information about the link training time, and then some optional requirements for receiver time, local and remote receiver time, counters for link failures and link losses, and then a status of communication ready. And so these are needed for different open alliance tests. Also polarity detection and correction, and then a FEC, forward error correction counter, to give you statistics on how much the communication is actually relying on the error correction. There's additional specifications in development for system implementation, the EMC test specs for the transceiver and ESD suppression, and then some compliance tests for the physical coding sublayer and the PHY control. And you can find this latest status for all of these and even more detail of the other tests that I just outlined at opensig.org. You can, I believe membership now is free, so you can join the Open Alliance and then have access to these specifications. MultiGBASE-T1 test tools. So our first tool is going to be the successor to the Radmoon 2, Radmoon 3. It's a MultiGBASE-T1 media converter based on Marvell's 88Q4364 PHY. So you will be able to connect between 2.5, 5, and 10 Gbase-T1 to the 2.5, 5, and 10 Gbase-T PHYs. You will not be able to mix speeds. 2.5 gig setting is on both PHYs, T and T1. They need to match. Otherwise, you'd need the need for buffering and other more complexity in the device than it really needs. User interface is very similar as well. You can configure the clock configurations and the status of if it's a master or slave, link speed configurations, status and activity, and then the SQI bar graph on the side. Other features is powered via barrel jack. These won't be able to be powered by USB 3. It's a very useful feature, very convenient on Radmoon 2, but the power demand or the current demand for these devices is going to be too high to expect that to work. We'll have the HMTD MultiGBASE-T1 connector. You'll be able to register read registers of the PHY over USB, either using Vehicle SPI or our open source API. So all of the diagnostic information that I just mentioned from the Open Alliance, that would be available either using our software, or if you want to write your own software and receive the information over USB. There's also an extra button we had on here that will be user-defined button, and you could use that to create your own test modes, or use it to switch the device between different test modes if you write your own software using our API. And additionally, what's next? We're already working on the MultiGBASE-T1 SFP with the HMTD connector, as well as adding some MultiGBASE-T1 to our Automotive Ethernet switches, and taps and loggers are also in our development pipeline. And they're still early enough that they can influence some changes. The media converter and the SFP, the use cases of those are pretty fixed, but for taps and loggers, it really helps to understand our customers' use cases. So if you're able to share any information about what the types of ECUs you'll be testing, the use cases or test cases that you need, consult us. If you can consult us, we can discuss what we have in development that will support your needs, or we can make adjustments if we think that we can solve a problem for you that you might not be able to do with off-the-shelf components. So is 10 gigabits per second fast enough? Well, apparently not. Enough thought not that work began on 802.3 CY, physical layer specification and management parameters greater than 10 gigabits per second electrical automotive Ethernet. So performance characteristics of an automotive link segment and a PHY, 25 gigabits per second point-to-point operation, this time only supporting 2 inline connectors instead of 4, and on 11 meters of automotive shielded twisted pair cabling instead of 15. So there were some trade-offs that were made to go from 10 gigabit to 25. Initially, this 802.3 CY had some verbiage in it about higher speeds than 25, I think 50 and 100. I think back in second quarter time frame, they reduced the scope to 25 gigabits per second. So that's all the material I have today. Hopefully it answered some questions that you may have had, and or maybe it's raised some questions that you didn't know you have. So let's take a look at the questions and answers, or Q&A, and also go back through the chat as well. I see a number of information in there, or questions in there. So see a question from Ed Wallner. Hi, John, from MultiGig Ethernet. Do the same secure communications apply as in TLS, IPsec, and MACsec? Well, TLS and IPsec are higher layer security. So IPsec's layer 3 and TLS is layer 4. So that's really above the well above the PHY. Now MACsec, yeah, the devices will support MACsec at the devices will support MACsec. Everything our media converter with the Rev silicon for Radmoon 3 will not support MACsec. It's an earlier version of that PHY, but the production intent version of that PHY will support MACsec, and I expect it's important enough to all the OEMs that I'll be surprised if there are any MultiGBASE-T1 PHYs that do not support it. Okay. Nice shot. Do you have devices that can be functionally similar to the VN5620A? I guess I recognize the part number, but I recognize the vector part number. I don't recall what that is off the top of my head. If you're talking about a tap, we will have MultiGBASE-T1 taps and 1 gigabit taps.
It's a 100 base to 1000 base T1 media converter. 100 base T1 / 1000 base T1 media converter.
Yeah,
So
that would be the Radmoon 2, I
yep,
believe.
that one too.
Yeah. Okay. Thanks, Harpin. Mark Hugh. Hi, Mark. I've got 3 questions here. Is SFP Plus an automotive grade interface? I don't believe it is. We're building it into our devices so we can support SFPs, but I think it's more of a you'll see it more in test racks and industrial applications. But in terms of supporting MultiGBASE-T1, it'll support it, but the interface itself is not automotive. Slide 18 states MultiGBASE-T1 supports SerDes interface such as SFP Plus. Let me go back to page 18. I'm not. So the SFP Plus we're using as an interface between the PHY and like our test equipment. I guess I'm not sure how it would. Maybe I'm not following the question. Let me jump to number 3. Do you have Radmoon 3 for SFP Plus and TX? No, a Radmoon 3 does not have SFP Plus. The PHY is designed into the board, into the circuit board design. Let me go through the chat here. Some questions. Recording be available later. Oh yeah, Arpin answered that. So Paul, how are collisions maintained with that much traffic? Packing collisions are being monitored. Only ask because even in my 2022 Yukon, my rear camera will stay on longer periods and have. Okay, so in automotive Ethernet, at least 100,000 in MultiGBASE-T1, there are no collisions. It's a switch network. Everything is point-to-point. Collisions are managed by switches that will buffer frames and queues and to ensure that there are no collisions and no information is lost. The slower 10 base T1S, the 10 megabit, that is not a switch network. That is a multi-drop network or a bus network. That does have, actually, that does not have collisions either. That has something called PHY level collision avoidance, and it's kind of like a schedule of, you have a time window where each device on the network can use the net bus, and the other devices are not allowed to transmit. So there are no collisions in that either. Oh, thank you. ZOWI stands for 10 gigabit attachment unit interface for ZOWI. Will there be sleep wake up capabilities for multi-gig PHYs? Yes, they will support this. They would have to. Oh, I see Steve. I didn't realize. Hi, Steve. Thanks for clearing that up. 802.13 3 CY 1500 gigabit objectives were going to be supported by PHY bonding. Multiple 25 gig PHYs. The task force felt that creating the PHY bonding would add additional year to the project. So those objectives were dropped in June. New project will be defined for supporting. To define PHY bonding could be done at a later date, and no change made to 25G-BASE-T1. Please elaborate a bit on the harness defect detection in TC15. So as I understand it, the PHY sends out a signal at different frequencies and looks for at what frequency that signal is reflected, or it has the maximum amplitude of the reflection, and that would correlate with the length of the wire that wave or that signal has traveled. And so it's basically measuring the time it takes for reflected reflected signals to come back from the open or the short. So I can't say how it's been implemented by all the semiconductor suppliers, but it's usually a bunch of registers that you need to configure and then probably write and read to in a certain sequence, and then the that information is in the registers, and then you have to go through, just do some simple math on it to calculate how many meters the fault is out there. In a lot of cases that may be abstracted away in an API given to you by the semiconductor manufacturer, so you don't have to go down into, dig deep into the register spec and to get that feature to work. I don't see any other questions.
Thank you, John. Thank you, everyone, for joining. Look for our email for our next webinars, and thank you all. Bye.
All right, thanks.